Welcome everybody to Algebra 2, Section 4.3, Solving Quadratics by the Square Root Method. So let's talk about radicals and let's just review them a little bit here. We practiced radicals back in Unit 1 as well. A radical is any expression with a square root, cube root, etc. And the radical symbol is this. I often personally draw it like this with a little tail at the end. It's completely optional which one you do. You'll see me doing the one on the right as just a matter of preference from what I've been doing for a long time. Listing the first 20 perfect squares we're going to do here, and knowing the perfect squares is incredibly helpful when you're trying to simplify square roots. And it'll be incredibly helpful for today's lesson as well as some future lessons as well. So I encourage you to work on memorizing these perfect squares, or at the very least, remembering how you can generate the list by squaring different terms. And there's no exact science for as far as how many perfect squares is good for you to remember. For example, when I was in high school, I memorized the first 25, but this is the first 20, and really there's no perfect number that's like, oh, it should be this or that, but you should at least be able to recognize a decent number of perfect squares. It'll be incredibly helpful to you. And if you don't panic, because you can still figure out the answers even if you don't recognize them instantly. So without further ado, let's write the first 20 perfect squares. So 1 squared is 1, 2 squared is 4, 3 squared 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, 15 squared is 225, 16 squared is 256, 17 squared is 289, 18 squared, I almost said 19 squared, 18 squared is 324, 19 squared is 361, and 20 squared is 400. And once again, you could keep going if you truly wanted to. There's nothing wrong with that, nothing necessarily right about it either. So when we're simplifying radicals, we have one of two cases. Either that it's a perfect square, in which case the problem's pretty straightforward and quick, comparatively to non-perfect squares, where you have to break the radical down by using the largest perfect square. We do want to find the largest such perfect square, and how we would do that is you would take the radicand and start dividing it by perfect squares. So for example, 200, or I'll get to that actually in a moment. I'm speaking a little ahead of myself here at this point. And now for both cases, it's important to note that if there's a coefficient out in front, it is multiplying with the radical. So that means anything that you take out as our simplify out to become a regular number, not a radical or a square root, then it'll multiply with that coefficient. So write each expression in simplest radical form. The square root of 49, 49 is a perfect square, so it is 7. Square root of 225 is 15. And 2 times the square root of 144 is 2 times 12, which is 24. On number 4, we have a fraction. So this is really the square root of 4 over the square root of 9, and the square root of 4 is 2. The square root of 9 is 3, and so you get 2/3. A lot of us might end up starting to skip this middle step here and just go straight from the first to the end. That's perfectly fine as well. On number 5, the square root of 1 is 1. The square root of 81 is 9. So there I skipped that step as well, like I mentioned on the last one. On number 6, the square root of 36 is 6. The square root of 121 is 11. On number 7, 112 is not a perfect square. So this is where we start getting that case 2, the non-perfect squares from up above. And so what we do is we look for 112 and we say, okay, the first number that could possibly divide into 112 is 100. And I say that because, the first perfect square that could possibly divide into 112, not the first number, but the first perfect square. And I say that because 121 is bigger than 112, so it couldn't possibly divide into 112. Now 100 could technically possibly divide into 112 because it is smaller. It does not divide into 112, however. And so we go on to the next one. We try 81, then we try 64, and so on and so forth until we find it. But we want to go biggest to smallest. That will make our life a lot easier in cases where a number has multiple perfect squares that are factors of it. The biggest such perfect square that is a factor of 112 is 16. And so then we say this is really the square root of 16 times the square root of 7. We get 7 by saying that 16 times 7 is 112. And because 16 times 7 is 112, it's also true that we can state that the square root of 16 times the square root of 7 is the square root of 112. The reason why this is helpful for us here is because square root of 16, well, 16 is a perfect square, and we can actually do the square root of 17. So we do the square root of I said 17. We can do the square root of 16, and the square root of 16 is 4. So we get 4 square root 7. And that ends up being our answer. Number 8, the square root of 245. I would take a moment to pause the video, try these next few on your own, by the way. Continuing on, though, the square root of 245, the biggest perfect square that goes into 245 is 49, and it goes into it 5 times. And so we would then call this 7 square root 5. Number 9, we just have a 5 out in the front, but that doesn't affect us looking for biggest perfect squares. The biggest perfect square of 72 is 36, and it goes into it 2 times. So this ends up becoming 5 times 6 times the square root of 2, and 5 times 6 is 30, so it's 30 square root 2. On to number 10. Oops, flipped too far there. The biggest perfect square that goes into 45 is 9. So we just have 9 times the square root of 9 times the square root of 5. This gives us, 9 times 3 times the square root of 5 when we do the square root of 9, which is 27 times the square root of 5. On number 11, the biggest perfect square that goes into 250 is 25. So the square root of 25 times the square root of 10, which then gives us 5 square root 10. Number 12, we have 3 times the square root of 578. So that's 3 times the square root of 289. 17 squared times the square root of 3. So that's 3 times 17 times the square root of 2. Oh, I said 3. My apologies, that should have been a 2 up above. Because the square root of 289 times 2 is the square root of 578. And so then we end up saying, well, 3 times 17 is 51, and 51 times the square root of 2 is our answer. Now let's move on to applying this to new material. So this is old, this is review what we just did here. And we're going to use these square roots to solve quadratics. And how this works is if a quadratic equation can be written in the form of x squared equals n, aka the square term equals a number, then the quadratic can be solved by using the square root property. And if x squared equals n, then it must be true that x equals positive and negative n. The reason we say this is the case is because if we have x squared equals 9, for example, and we were to square root both sides, we say that x would equal not only 3, but also x would equal negative 3. Because if we were to plug 3 in for x and square it, you get 9. If you plug in negative 3 for x and square it, you also get 9. So on the previous page, we didn't take positive and negative scenarios, but only the sign which we were given, which was positive in each of them. Here, we're taking both scenarios, the positive and negative, because we're solving an equation. And so when we are doing the square root to undo a square, we will have to take both cases, the positive and negative cases. And we commonly write this as plus or minus or positive negative 3. And that just is a shorthand way of writing these two answers. And so it's the same answer, same thing, as far as x equaling 3 as well as negative 3. So our first step when we do this is to rewrite the equation in this form, aka get whatever's being squared by itself. Isolate the squared term. And so it might not be a bad idea to write that in here, that you isolate the squared term. And notice I'm not just saying get x squared by itself or isolate x squared, because sometimes it won't just be x squared. We'll encounter that starting on problem number 22. Then we take the square root of both sides, and this undoes the square. Just similar to how we undo addition by subtraction or we undo division by multiplication, we undo squares by square rooting. And then we simplify the radical as needed, placing that positive negative symbol to indicate there's both answers, like I mentioned up above. Now, with it being able to rewrite like this, that means that there's no bx term. So we'll note that with our quadratics when we do solving by square roots, we see normally it's ax squared plus bx plus c, but if we had, and that would equal 0, but if we have a bx here, then we won't be able to write it in this format because there's no x term there. And so in order to solve it by square rooting, you have to be lacking or missing that x term. So you'll notice on these examples for 13 through 24 that none of them will have a bx or an x term there. So on number 13, we're supposed to solve, on this set from 13 to 24 rather, we're supposed to solve by using the square roots method. So on number 13, our first step is to get whatever's being squared by itself. X squared is being squared, so we add 64 to both sides and get x squared equals 64. Now that our square term is by itself, we undo the exponent of 2 by square rooting. And the square root of x squared, those undo each other, just like addition, subtraction, or multiplication, division, and we get x. And on the right-hand side, the square root of 64 is positive and negative 8. We have to once again include positive, negative, because they're both possible answers for this equation, because if we plugged either one of them in, they would work. Number 14, x is being squared, not the 7, but just the x is being squared. And so we have to get rid of the 8 and the 7. We get rid of the 8 first by subtracting 8, and we get 7x squared equals 7. Then we divide by 7 on both sides and we get x squared equals 1. Now our square term is by itself, and now we can square root both sides to undo the square. Doing this gives us x equals positive and negative 1, because the square root of 1 is 1. On number 15, once again, x is being squared, so we have to get rid of the 81 and the 5. We undo the addition first by subtracting, and I get 81x squared equals 16. Now I divide both sides by 81, and I get x squared equals 16 over 81. They have no common factors other than 1, so they can't reduce. As we square root both sides, we get positive and negative 4 over 9. So very similar to on the previous page when we had fractions. They happen to both be square roots, and they will be today as well. And we can say, oh, the square root of 16 is 4, the square root of 81 is 9. Number 16. X is being squared, so we need to get x by itself by subtracting 1 and dividing by 8. So if I subtract 1, I get 8x squared equals 16. And if I divide by 8, I get x squared equals 2. So then I square root both sides to undo the square, and I get x to equal positive and negative square root 2. Now, I can't simplify the square root of 2 anymore because the only factors that go into 2 are 1 and 2. And taking out the square root of 1, or calling it the square root of 1 times the square root of 2, doesn't help us at all because we didn't make our radicand, the number inside the radical, the 2 here, any smaller. So this is our answer. So for non-perfect squares, our answers will involve the square root just like they did on the previous page. 17, we undo the squared term, which is x squared, or excuse me, we get the squared term by itself, which is x squared, by adding 9 and then dividing by 2. So we have 2x squared equals 64. Divide by 2 and x squared equals 32. Square root both sides, undo the square, and we get x equals positive and negative square root 32. We now need to simplify the square root of 32 though, because we can simplify the square root of 32. And it's positive negative square root of 16 times the square root of 2, which becomes positive and negative 4 square root 2. And then this is our answer. So the right side, we're doing the exact same thing we did on the previous page, but now we're just, once we get to this point, we're doing the exact same thing we did on the previous page. We just had this plus or minus in front, and we had to isolate our squared term beforehand. Number 18, we have to undo the multiplication of 9 and addition of 3. So we'll start by undoing addition of 3 by subtracting 3 and get 9x squared equals 108. I'll then go ahead and divide by 9 and get x squared equals 12. If I square root both sides, I get x equals positive and negative 12, square root of 12, which I'm just going to go ahead and in this step call it square root of 4, square root of 3. So I'm kind of omitting an extra step there that I did last time, where I rewrote positive negative square root of 32 here, and instead went straight to this. So I went from here to here. If you want to keep writing this step in there, that'd be perfectly fine if you wrote x equals positive negative square root of 12 there. So now I go ahead and continue simplifying this by saying the square root of 4 is 2, and I get 2 square root of 3. Moving on to number 19 here, once it kind of loads. Sometimes moving it around helps it load. There we go. Number 19, we have to undo the 4 and the negative 3. We undo the 4 first by subtracting 4, and we get negative 3x squared. That negative stays with the 3, and we end up getting negative 3x squared equals negative 81. Dividing both sides by -3 gives me x squared equals 27. So now if I square root both sides, I get x equals positive and negative square root 9 times the square root of 3 as I seek to simplify that right-hand side. And I get positive and negative 3 square root 3 as my two answers. Number 20 here, we undo the addition of 10, and then we'll divide by 5, and I get 5x squared equals 300. Dividing by 5 gives me x squared equals 60. Square root both sides, and I get x equals positive and negative square root 4 times square root of 15. I was buffering there while I was thinking of the perfect squares that would go into it. And x equals positive and negative 2 square root 15. Number 21, 9 plus 10. We have to undo the 1, and then we'll have to undo the multiplication of -1/2. And so I undo the 1 by subtracting it, and I get -1/2 x squared equals -40. And I will showcase the math that I'm doing here to undo the -1/2. We undo fractions multiplying with variables, not by dividing, but rather by multiplying by its reciprocal. And so I'll multiply by -2/1. Where the negative is completely irrelevant. What matters is the fraction as a whole is negative. And so we end up getting negative times a negative, which is a positive, and we get positive x squared. Whereas on the right-hand side, we multiply -40 times -2 and get positive 80. I then square root both sides, and I get x equals positive and negative square root 16 times the square root of 5. So this becomes positive and negative 4 times the square root of 5. Number 22, as I mentioned earlier, I said in step 1, don't just say rewrite the equation as x squared equals n, but rather clarify that it is isolating the squared term. And this is why. Now our x is not being squared, the 2 is not being squared, but rather that entire quantity or parenthesis is being squared. So this is actually isolated. 23 is not because there's a 3 outside the parentheses that's being squared, but in 22, the squared term is isolated. So we go ahead and go to step 2 of square rooting both sides. And the square and square root undo each other, as I've been mentioning, and I get x plus 2. I get the entire thing inside. I don't have to take the square root of x or the square root of 2. The square root undid the square, and I'm left with the radicand, or what was inside, which is x plus 2. On the right-hand side, I get positive -7. So now I notice, oh, wait a second. My x is not actually by itself here, like it has been on the previous 9 examples. So I still have to subtract 2. Now a common mistake I see is the following, so don't write this down, is we'll say subtract 2, and we'll call this x equals positive -5 and move on with our merry way. But that's just not accurate. And if we were to plug in both 5 and -5 back into our original equation, we'd find that one of them would not work. And it's not because it's extraneous, it's because it's the wrong number. And so what we actually have to do here is we have to say that there's 2 cases. That we have x plus 2 equals 7, the positive version, as well as x plus 2 equals -7, the negative version. And the reason we have to clarify this is because we've had the positive negative versions the whole time. We talked about that at the beginning, when I said, at the beginning of this page, I should say, when I went up here and said, hey, we had x equals 3 and -3, we just often write it as positive -3, but they really mean the same thing. But we have to clarify this time because now as we seek to subtract 2, I get x equals 5 for one of them, which was one of the answers I got. I got positive -5. But in this other version, as I subtract 2, I get x equals -9. Very different than the -5 I got before. So my two answers are not positive -5, but rather 5 and -9. And if I were to plug both these numbers back in, either of them and both of them would work. So when you have an opportunity where you can actually combine like terms at the end, we have to separate this positive negative into our 2 cases, the positive and negative cases, before continuing and actually combining these terms when you subtract the 2 and combining 7 and -2 as well as -7 and -2. So once again, this will occur when x is not by itself, and these are terms that we could combine. On number 23, our squared term is not by itself because 3 is multiplying with that squared parenthesis. So I divide both sides by 3, and division undoes multiplication, and I get 1 times the quantity of x minus 1 being squared, and I don't have to write the 1, so I won't. And that equals 6. Now that my squared term is isolated or by itself, I'm going to go ahead and square root both sides to undo the square, and I get what's inside, which is x minus 1. And that equals positive negative square root of 6. Square root of 6 cannot be simplified anymore, and so we just leave it as the square root of 6. We still have to get x by itself, but however, we do not have to write both cases this time as far as x minus 1 equals square root of 6 and x minus 1 equals negative square root of 6. The reason why is if we add 1 to both sides, we cannot combine this 1 and the square root of 6. So we don't have to worry about writing them as two separate cases. You certainly could, and it wouldn't be wrong. But instead we have 1 plus or minus the square root of 6. And now you might be wondering, Mr. Kossel, why did you write the 1 before? Would it be okay if I wrote plus or minus square root of 6 plus 1? And while technically accurate, it is often confusing because then we're unsure if this plus or minus is only on the square root of 6 or also saying that the 1 can change signs. And then we have both scenarios of a positive and negative 1. And that's just not the case. We know that the 1 is positive because we added it. It's not negative. We're certain of that. So instead, it is common and desired, and you will need to write your answer like this. 1 plus or minus square root of 6. That is how I expect the answer to be written, with the constants or any non-square root term to be written beforehand, before the plus or minus. That way we are stating very clearly, explicitly, that the 1 is positive, but only the square root of 6 is both positive and negative. So it's 1 plus the square root of 6 and 1 minus the square root of 6, written as a shorthand like this. And because 1's a square root and 1's not, we cannot combine them. Number 24, we need to get our squared term by itself. We'll do this by dividing by negative 2. Negative 2 is multiplying. A lot of people would try and add 2 here, but 2 is not subtracting, it is multiplying. And so we get the quantity of x plus 7 squared divided by 20. Now our squared term is by itself, so we square root both sides, and I get x plus 7 equals the positive negative square root of 4 times the square root of 5. Now before I worry about subtracting the 7, I'm going to complete simplifying this side. And so I get x plus 7 equals positive negative 2 square root 5. Now it's not technically required that I complete that side before moving the 7 over. You could technically do them at the same time or one before the other, but I do encourage it to be done this way because I think it makes your life a lot easier and more straightforward and allows for less mistakes to be made from doing too much at once. So now if I subtract 7 from both sides, while 7 and 2 are like terms, 7 and 2 square root of 5 are not like terms. So it's not just a 2, it's a 2 times the square root of 5. That'd be similar to trying to say that you could do 2x minus 7 and call it negative 5x, which just is not the case. So instead we write the negative 7 before the plus or minus, and then write the plus or minus 2 square root 5, because we cannot combine the 2 square root 5 and the negative 7. And this is our answer. That wraps up Algebra 2, Section 4.3.